So here is a video review of titrations. The idea of titrations is that we are carrying out some kind of neutralization reaction in order to find equal numbers of moles of hydrogen ions and hydroxide ions if we're doing acid-base neutralizations. And that helps us figure out how much of something we have when we don't know. So let's say that I have some acid that I've added to my flask here. I don't know the concentration of the acid, but let's say that it's HCl. So I know that it's monoprotic. Monoprotic means that it only has one hydrogen in it. So I have hydrogen floating around in here, and chloride ions and hydrogen ions and chloride ions, but I don't know how many I have. But I do know that I have one hydrogen for every one chloride. In the burette, we're going to add a standardized solution. That just means that we know what its concentration is because we made it in the lab. So this is my standardized sodium hydroxide solution. Sodium hydroxide is the most common base that we use in acid-base neutralization. And I'm going to fill up my burette with my standard sodium hydroxide because I know what I made. I know that it's 0.10 molar, or in IB lingo, moles per cubic decimeter. This is what I have filled up my burette with, 0.10 moles per cubic decimeter sodium hydroxide. So what's going to happen is this. I'm going to drip some of my sodium hydroxide out of the burette into the flask. The NaOH is going to react. The OH is going to find an H, and they are going to cancel each other out and make water, which is both acid and basic, or neither an acid nor a base, but it's neutral. So this is a cool thing that happens. I've got a neutral molecule where I used to have a very acidic and a very basic polyatomic polyatomic ion. So now I'm going to drip out a little bit more, and I have some more Na pluses and OH minuses. They're going to again react with the acid that's in the flask, and voila, these guys are going to cancel each other out. I've got more water. I've added a indicator in here, so I've got a color change about to happen. So this, I like to use phenolphthalein just because it's a crazy spelling word. So I've got phenolphthalein in here, which is colorless in an acid. So my phenolphthalein right now is still colorless because I've got this H plus makes it colorless. But it turns this beautiful bright pink in a base. So now I'm going to add a little bit more sodium hydroxide, a little more sodium hydroxide. This hydroxide is going to bind to this H plus. I have another water. I have a perfectly neutral solution right now. If I allow one more little drip of sodium hydroxide in here, NaOH, I now have more OHs than I have H pluses. That is going to turn the whole thing. I don't have pink. So now it turns pink, and I know to stop. So I'm going to measure how much of the sodium hydroxide did I let out of the burette in order to neutralize. We actually take it one drip further than neutralization just so we can see that pink color change. I'm going to figure out how much sodium hydroxide I released. Let's say that I released 6 milliliters of sodium hydroxide. This is the concentration. I started with, let's say that I had 20 milliliters of that acid to start in my flask. So now I can use M1V1 equals M2V2. We're going to do, V2. A little more practice with this, so don't panic about getting it entirely on the slide. My base needs to equal my acid because we're neutralizing them. They have to have equal moles of H pluses and OH minuses to make all the waters. So my base's molarity is here, 0.10 molar. The volume that I added is here, 6 milliliters. Set that equal to M2 of my acid. I don't know. That's what I'm trying to figure out by doing all this stuff. V2, I put in 20 milliliters. Solve for M2, divide both sides by 20 mils. That cancels out. I have M2 equals, here's the magic of the units, milliliters on top and milliliters on bottom cancel each other out. I'm left with molar, which is good because I'm trying to find the molarity, the concentration of that acid. Calculation-wise, I'm going to do 0.10 times 6 divided by 20, and that's going to give us 0.03. Concentration of the acid in the flask was 0.03 molar, or in IB lingo, moles per cubic decimeter. All right, let's do another one. Let's say that I went from 0 mils to 12 mils in my burette. My standard solution was, again, 0.10 molar sodium hydroxide. Let's say this time I added only 10 mils of hydrochloric acid. Let's solve for the concentration of this unknown hydrochloric acid. We're again going to set our base equal to our acid. The molarity of the base is here. The volume of the base is here. I went from 0 down to 12. That means 12 mils of the sodium hydroxide was released into the flask to neutralize that acid. M2 of the acid, I don't know. That's what I'm solving for. V2 of the acid is here. So we're going to do 0.10 molar sodium hydroxide times 12 mils of sodium hydroxide. Set that equal to, I don't know, the concentration of the acid times 10 mils of that hydrochloric acid. Divide both sides by 10 milliliters. Milliliters cancels out. Concentration is going to be 0.1 times 12 divided by 10. Takes us right back to 12 milliliters. Good. Good. All right. So let's do it without a picture. Let's say that I've got 83 milliliters of 0.45 molar sodium hydroxide solution needed to neutralize 235 milliliters of hydrochloric acid solution. This is going to be my V1. This is going to be my M2. This is going to be my V2. And this is what I'm trying to find. The concentration of the hydrochloric acid is my unknown. That's what I'm solving for. M1 V1 equals M2 V2. M1 is, well, that should be a 1, not a 2. 0.45 molar times 83 milliliters is going to equal M2. I don't know. And then V2 is 235 milliliters. Divide both sides by 235 milliliters. Milliliters cancels out. Divide by 235 milliliters. Milliliters cancels out. Molar is all that's left, which is good because that's what I'm looking for. 0.45 times 83 divided by 235 is going to give us a concentration of 0.15, lots of digits. I need to round to only 2 sig figs. I've got 2, 3, but 2 is less than 3. So we're going to keep 0.16 molar is the concentration of that unknown acid. All right, let's do one more. I've got a V1, I've got an M1, I've got a V2. I need to solve for M2. So we're going to set up our equation as always. M1 V1 equals M2 V2. 0.75 molar base times 38 mils is going to equal, I don't know, the concentration times 155 mils. Divide both sides by 155 mils. That cancels out. Mils on top, mils on bottom cancels out. 0.75 times 38 divided by 155 is going to give us a molarity of 0.1838. Lots of digits. I'm going to round to 2 sig figs. 0.18. 0.18 molar is the concentration of the hydrogen ions that are needed to neutralize the hydroxide ions in the sodium hydroxide. But this is where things get a little quirky with this question because my acid is actually diprotic. I don't have one hydrogen, I have two hydrogens in sulfuric acid. Every one sulfuric acid actually has 2 hydrogens. When I do M1, V1, M2, V2, I'm figuring out how much hydroxide is matching how much hydrogen ion. So I do have here the concentration of the hydrogen ions that were in the acid, but I don't actually have the full concentration of that acid. I only have the concentration of the H pluses. But that's okay, because I can use my formula here to figure out that I have 2 H pluses in every one H2SO4. We have 2 H pluses in every one H2SO4. So if I take my 0.18 molar hydrogen ion concentration divided by 2, that's going to give me 0.090 moles per cubic decimeter concentration of the acid, because there's 2 H's in every one of those. So if I take this multiplied by 2, I get back to that, which makes sense. So this is the concentration of the acid, H2SO4. This is the concentration of the hydrogen ion, the H pluses, that are in that acid. All right, let's do an IB style question. Ethanoic acid is diprotic. That means it's got 2 hydrogen ions stuck to it. We're trying to figure out what is the X in the hydrated version of the formula, which is here. What even is X? This is our ultimate goal. We're going to do that we're going to figure that out by titrating with a known mass of the acid with this known concentration of sodium hydroxide. This is our mass. We're going to come back to this much later. It's dissolved in water. This is our total volume of the acid solution. I'm going to take from that total volume little samples. I'm going to titrate these little samples. That's going to be important later. So this is our total volume. These are our all clotted out volumes. So here is our data. We're asked first to figure out uncertainty of the volume of sodium hydroxide added. So to figure out how much volume was added, I have to subtract. So if the burette started at 0 and went down to 13, 13 minus 0 is 13 cubic centimeters of sodium hydroxide. Here my 12.70 divided by, subtract. I'm going to subtract. If I started at 13 and I drift out to 25.70, that means that 12.70 cubic centimeters of sodium hydroxide was added in tidal number 2. How about in tidal number 3? 38.20 minus 25.70. That's going to give me 12.50 cubic centimeters. Uncertainty of the volume. Since I subtracted to figure out the volume each time, I'm going to have to add the uncertainties of the 2 pieces of data that I subtracted with. So the uncertainty of the volume, because it's the difference of 2 pieces of data, the uncertainty is going to be the sum of the uncertainties of each of those data points. The uncertainty is going to be plus or minus 0.10 cubic centimeters. That's our uncertainty. So now we're going to do a little bit more math with all this stuff. I want the average volume of titrations 2 and 3. Why not titration number 1? That's because we always throw it out. We don't worry about titration number 1. That first titer just shows us how close is close, so that we know when to slow down with titers 2 and 3. These are going to be far more accurate. This is our how close is close. So average volume 12.70 plus 12.50 divided by 2 is going to give us 12.60 cubic centimeters of sodium hydroxide. And now we need to figure out also in moles. So I've got my cubic centimeters done. Now I need to turn that into moles. We do that using the concentration. So I know that my sodium hydroxide is 0.100 moles per cubic decimeter. I need to figure out, if I have this many cubic centimeters, how many moles is floating around in there. To do that, I'm going to convert my cubic centimeters into cubic decimeters. I do that by dividing by 1,000, because there are 1,000 cubic centimeters in each 1 cubic decimeter. So my cubic centimeters, top and bottom, cancel out. We're going to divide by 1,000. There's 1, 2, 3 zeros. We're going to go backwards 1, 2, 3 decimal places. And so I have 0.01260 cubic decimeters of that word of converted to math is multiply, of my 0.100 moles per cubic decimeter sodium hydroxide. The magic of my labels right here. So I have dm to the plus 3 times lots of stuff dm to the minus 3. Since I have the same base different exponents, I can add my exponents. Plus 3 minus 3 is 0. Anything to the 0 power is 1. I totally just canceled out those labels. All I have left is moles, which is great because that's what I'm trying to find. 0.01260 times 0.100 is going to give us 0.00126 moles of sodium hydroxide. You can do it in a calculator, or if we're multiplying by a 0.1, we just need to move our decimal place backwards, one to the left. So this is my answer in moles. This was my answer in cubic centimeters. All right, so we're going to take that number over to the next screen. So I need to figure out the amount of ethane dioic acid that reacted with my average volume of sodium hydroxide. The average volume was at 12.60 cubic centimeters, which was equal to 0.01260 moles of sodium hydroxide. This was my average volume, which is equal to that number of moles. So to flip my moles of sodium hydroxide to the moles of the acid, I'm going to use the balanced equation. So I've got 0.00126 moles of sodium hydroxide. I found that again on the previous screen. That's that guy right there. I'm going to flip that into ethane dioic acid by using the mole ratios from the balanced equation. So I've got 2 NaOHs and I've got 1 HOCOOH. So this times 1 divided by 2 gives us, in scientific notation, 6.3 times 10 to the minus 4 moles of ethane dioic acid, or we could, in not scientific notation, 3 zeros. I should keep a few more sig figs in here. That many moles of ethane dioic acid. So that's this first part. Now I want to figure out the moles of ethane dioic acid present in 250 cubic centimeters of the original solution. Isn't that what we just found? No, it's not, because this is the moles in each titration. Remember that in each titration, I pulled only 25 cubic centimeters out of my original 250. So I took this and I chunked it into tenths to do each titration. So to go back to my original, I'm just going to have to multiply by 10. This is how much in each 1/10 of the original solution, which means that I just need to scale it up by 10 to get back to that total original solution. Multiply by 10, I'm just going to move my decimal place 1 to the right, so I have 0.00, only 2 instead of 3, 6300 moles of that ethane dioic acid in my original total whole sample. That's part 2. This should be part 3. Molar mass of the hydrated ethane dioic acid. So now what we're going to do, molar mass is always grams per mole. Molar mass is always grams per mole. Go back to that last screen. I have 0.795 grams. 0.795 grams divided by moles. That's what I just found here. 0.006300 moles. 0.795 divided by 0.006300 gives us 126.2 grams per mole. That's the molar mass of my hydrated ethane dioic acid. How am I going to figure out now what X is going to be? Well, we're going to use this molar mass, and I'm going to subtract this mass to figure out what's left over here. So I'm going to take my HOOCCOOH. That's going to be 2 times 1.01 plus 4 oxygens plus 2 carbons is going to give me a total mass of 90.04 grams per mole. So this is what the molar mass of that ethanoic acid ought to be, but we got 126. The difference between this and this is that water. So 126.2 minus 90 is going to give us about 36.16 grams. And if I convert those grams into moles of water, 2 H's and an O, 1.01 times 2 plus 16 is going to give me 18.02. 18.02 grams per mole. 36 divided by 18 is 2. That means that this formula here is going to be 2. X is equal to 2.